Excelente, ya estamos listos. Muy bien, pues de nuevo una disculpa aquí, un inconveniente. Muy bien. Okay, so let's start. First of all, I would like to review a few comments that we made a few classes ago. So remember, so we define what is a smooth structure on a topological space, meaning what is the definition of a manifold. So it was in terms of an atlas. And also you did an exercise in R with two different atlas, but that they were diffeomorphic. And at that time, I mentioned the possibility for a manifold to have two actually disjoint smooth structures. And I mentioned that the first example of such behavior was given by Milnor in 1956. And it was on the 7-dimensional sphere. So there, he proved that the S7, the seventh sphere, has a different smooth structure, which is not related to the usual one. So this is what exotic will mean. Exotic means it is a space that has a canonical smooth structure. Euclidean space, the spheres, they always have the canonical structure. On Euclidean space, the usual one using the one short and the identity map. And on the sphere, we have the atlas given by two shards induced by the stereographic projection. So in 1962, they show that Rn does not admit any exotic structure except for n equals to 4. So R1 only has one smooth structure, the same for R2, R3, and so on. But he was not able to show that on R4, if it's possible to have only one structure, the canonical one or a different one. So it was until the 80s that Friedman proved that actually R4 admits an exotic smooth structure. And so this is like the history. There is more work than the one that I'm just writing out here. Basically, there is a more or less classification of all of the distinct smooth structures on R4. And I believe that you can have infinitely many smooth structures on R4 that are not diffeomorphic. On S7, there are finitely many. I don't remember the number, but it is well known how many structures do you have on the 7th sphere. And on R4 is going to be uncountable many of them. Or countable. I think there's a countable set of structures there. Okay, so now we will move to the topic of today, and we will look at the tangent space. Okay, this is a very important topic. It's very related to the smooth structure of the manifold, and it is very fundamental in our study of manifolds. So again, we have a manifold M, and I have a point. In order to define the tangent space, first of all, it is important to know that this is a local thing. So this is local. So it will depend only on local information about the point. Okay, we will define this space. It's going to be a vector space. Remember, note that we have a point there, P, a fixed point. And this space that we're going to define depends only locally on P. We will show that this is an n-dimensional vector space. So it is going to agree, the dimension of the manifold is going to agree with the dimension of the space, of the vector space. And again, I'm just making clear that this will depend only on local data. Now, there are two ways to define the tangent space at a point. We have an algebraic way and also a geometric approach. I'm going to discuss first the algebraic approach, and then we will work out the geometric. So I'm going to simplify things, and I will consider my manifold to be Euclidean space for the time being, okay? And I'm going to define a new set. This set depends on the manifold and on P. This is not a standard notation. And what I would like to emphasize, I mean, this open set can vary. So AP is the set of functions that are smooth and defined on some open set that contains P. So the domain of the function can vary, okay? So U is some open set. Maybe I can take another function G, and it will be defined on a smaller set contained on U. And that will also be an element here. Okay, now on this set, we're going to define a relation. So I take two elements in A of B. So note that U and V don't have to agree. They are open sets in Rn that contain the point P. And we're going to say that those two functions are related if you can find an open set in the intersection. Know that this intersection is non-empty because the point P belongs to both. So the intersection cannot be empty. So the first thing, there is an open set on the intersection that also contains the point. And the functions, when I restrict them to this smaller set, they agree. Okay, that's my definition of this equivalence relation. And I hope that this definition of the relation emphasizes why do we consider this type of objects. This is not fixed, it can vary. Any open set that contains P. Okay. I just want to emphasize that here is when we are using calculus. F and G are supposed to be smooth. And so this is going to be an equivalence relation. It is not a hard thing to prove. So F related to G, by definition, is the same that G related to F. No problem there. Also, F is related with F. There's no problem there. And transitivity, there will be no problem. Finite intersection of open set is open. And then you're done. You have an equivalence relation on this set. Now, what is important is the set of equivalence classes. That's really important, and that's what we have here. And that's the notation that we use. So basically, there are functions defined, smooth functions defined on a neighborhood of P. And I have an identification, right? If two functions agree in a neighborhood, they represent the same function on this set, right? By the definition of the relation. This set of functions is called the germs of functions at P. So I have the germ of functions, right? Now, are there any questions here? No? So far?
No.
Let me make one comment here, because this is going to be useful later on. Take an open set in Rn. And make any point there. The germs of functions here is the same as the germ of functions in U. Okay? In principle, this set is different if I take Rn and if I take U. For instance, if U is a proper set, I'm talking about this U. If U is a proper set, take any smooth function on U. That function is not a smooth function on Rn. Right? So depending on the domain, you can have different things here. But in terms of germs, you get exactly the same thing. So the germs of function on Rn is the same as the germ of functions in any open set. Okay? Because this is all local data about P. Okay, now this set that we just defined, it is an R algebra. You can multiply the functions. You know that the multiplication of two smooth functions is a smooth functions. So you can do that with the representatives. So you can multiply germs of functions. In the same way that you can add smooth functions to get a smooth function, the same happens with the germs of functions. So this is a vector space that also has a product operation. So you have an algebra there. I want to make the following thing precise. Take two germs. I'm sorry. Take one germ with two different representatives, right? That means that F and G agree in a small open set about P. Then they take the same value, okay? So functions that represent the same germ take the same value at the base point P. This will be important later on, this observation about the germs. Now, all of the above, I just defined it on Rn, but you can also define that on a manifold. Above, we only use the concept of smooth function on Rn. And we have already studied smooth functions on a manifold. So you can define also the germs of functions at a point in a manifold, okay? Again, I will make the same observation that if you have an open set, and P is in U, we already saw that U is a manifold. Of the same dimension as M, and here the same as above. The germ of functions of P in M is the same as the germ of functions of P in the open set U. Right? Okay, now. So let's move on. So far we have only defined this space has equivalence classes, and all of this is to define a derivation. A derivation is going to be a map of this space. So it will be a map from the germs to the reals. That's going to be a derivation. Now, remember that the set of germs is a real vector space. So the first requirement for a derivation is that it is a linear map. So nothing good. And the second point is exactly what the word comes from. Derivation, we will like that it emulates the product rule of differentiation. The derivative of a product, you know what is the derivative of that. So the second point, a derivation must satisfy this condition. Okay? This product is from the algebra structure here. This product, and also this one, is the product of real numbers. Okay? And this observation that I made here is the one that I'm using here. Note that I'm evaluating G at P. This is well defined. It doesn't depend on the representative of this class. Similarly, for the other object, I'm evaluating the function at P and is independent of the representative in that class. Okay? So a derivation is a linear map that satisfies the product group of derivatives. Okay, now. So let's go to Rn. And for instance, what you know from calculus, this is a derivation. You take a smooth function, you take the partial derivative, evaluate it at the point, because you're evaluating on a point, you have this. It is linear, you know that the partial derivative of a sum is the sum of the derivatives, and you also know the product rule. So taking the partial derivative is an example of a derivation on the terms of function of P. Note this and this. Okay? So this is an abstract way of thinking about the partial derivatives or derivatives in general. But it's very useful, as you will see. Right. Up to this point, any questions? So, okay. So we have defined the terms of functions, which is an algebra. And now we define what is a derivation. So let's move on. From the definition, you can actually show that the derivation of a constant function must be 0. This is something that you know from calculus, like the concept of the limit, which is a difference. So the derivative of a constant is 0. But it so happens that you can prove that in this framework using only these two conditions. So let's go ahead and prove it. So C represents a constant function in the neighborhood of P. Then this is the same as 1 times T, 1 times C. And then you use the product rule and you get this, right? But then you have this is equal to this one. So that tells you that d of 1 is 0. Of course, I must say that C is a non-zero constant, right? So the derivative at 1 equals 0, and from there you can say that the derivative of any constant function must be 0. Okay? Again, I want to stress that, I'm saying a constant function, but I only care that it is constant in the neighborhood of P, because I'm taking the germs. Okay? Oh, well, also here I made a mistake. Here you can put, I wrote it for Rn, but we can do it for any manifold, right? So, let me put here M and M. We have already defined the germs in a manifold. Okay. And also let me do it here as well. Good. So the tangent space, and here, the same will hold for a manifold, but from now I really want to stay with Euclidean space for the moment. So the tangent space at a point is the set of all derivations. So I take a point in Rn, and we have defined the tangent space at P. Okay, again, I want to stress that we're defining something for a point, and it depends only on local data. And here we emphasize that it is only on local data. It depends only on what is happening near P and not beyond. So this is the tangent space in Euclidean space to a point. It's the set of all derivations. That's clear? Okay then, so let's continue. I'm not going to prove this, but you can show that you can add derivations, and you can also multiply by a real scalar. So the set of derivations is a vector space. over the reals. So we have a vector space here. Now, the important thing is, well, if it's a vector space, what is its dimension? You might suspect that the dimension must be the same as the Euclidean space, that is n. But well, this is something that we must prove. Okay? Now, note that in this space, you already know some of its elements. I mean, oops, sorry. You already know that you have the partial derivatives. This is the example that we did above. So at least you have those n derivations. So you can guess, and we would like that the dimension of this is n, and basically that it is generated by those derivations. But that, so we must show that. So the intuition is correct. The dimension is n. And we're going to prove this and actually show that this is a basis of that vector space. Right? So always keep in mind that a derivation is just a partial derivative or a linear combination of them. So let's prove this result that the tangent space at a point in Rn has dimension n. And again, we will prove a stronger statement since we will show that we have a basis. So for any j between 1 and n, we already have this. We saw in the example that this is a derivation. So remember, derivation, a linear map plus the product rule. So first, let's show that they are linearly independent. So consider a linear combination of them, that it is equal to the zero derivation. So these are scalars. I must show that all of the aj's must be zero. So now consider that function that we have used before, and we know that it is a smooth function for some L between 1 and n. So this is a C infinity function, right? Projection to the L entry. That's a smooth function, so it will induce an element in T terms at P. Well, for this function with respect to the zero, derivation has to be zero. Now, what about the right-hand side? So I have to take the partial derivatives of this function. But you already know that taking the partial derivative of this with respect to this function is delta JL, right? It's either 0 or 1. And it is only 1 when the indices coincide. So I get that the AL must be 0. So the set of all possible partial derivatives is a linearly independent set. So now we need to prove that any derivation is a linear combination of what we have here. So far, so good?
Yes.
Okay, so let's consider an arbitrary derivation. We already know that the RJs are smooth functions, so they are in the terms of function of P, and I'm going to call this number AJ, whatever this gives me. Right, so this is a real number. A derivation is a linear map from the terms of functions to the reals. So I have a real number. So we claim that this derivation, arbitrary, that we took, must be equal to this. This is what we claim. Okay? So we're going to show that we will take an arbitrary germ of functions and show that when we evaluate this derivation, we get the same number as when we use this derivation. Okay, now, so take any element here. Right? Now, up to this point, you can say that F is defined on some open set like this, right? Now we're going to use the Taylor series of the function about P. But remember that what can happen for the Taylor series, sometimes it doesn't hold on all of the domain of the function. It will hold on a smaller domain. And we know that F is infinity. So here is where this concept is also very useful, because maybe we need to shrink the domain of F when we express F as its Taylor series. Okay, so I have this expression, but know that X can be in a smaller set. In a smaller set where the Taylor series holds. F is defined on all of U, but the Taylor series might be expressed in a smaller set containing P. Maybe not on all of you, but a smaller set. Great. So I have that decomposition of F has its Taylor series. Okay, now keep in mind, I want to show this equality. On the left-hand side, I only have D of F, right? So I apply this, or if you want, and now because D is a derivation, you know that it is linear. This is a constant, I get 0. And then it is linear, so I take the derivation of this. But the derivation satisfies the product rule. So I only take the derivative here, evaluate plus, why do I get this 0? This 0, where does it come from?
Because all the G's are fixed, right? Like,
No,
we must take the derivative of them in here by the Leibniz rule.
oh, wait, yes, hold on. Like, this is wrong here. It's in X. It's a function, right? Not a number. So let's see. Jesus, again, please.
No, yeah, no.
So let's see. I take the derivative of f of p, which is a constant, and I get the 0. Next, I take the derivative. I'm going to take only one term. Of this product of functions. And now I'm going to use the product rule. So this is times this number plus, oh, no, sorry, this is incorrect. I have to evaluate that function at p, right? So it's going to be pi minus pi okay? Remember that we have to evaluate at p when we don't take the derivative, right? Now, what is going on the last thing? This is 0, right? That is 0. This, I don't know. I don't know what this is, but this function is 0. So I only get this, right? And that's exactly what I have here. This 0 comes from this constant function. And now, this, I have it here. So this 0 is this. Okay? Very good. Okay, now, again, we have to use the fact that the derivation is a linear map. So I will just take the derivation of xi minus the derivation of pi. Again, pi is a constant function, so that is going to give me 0. Oops. So at the end, I only get this. And now I make the substitution, giving my Taylor series, and I have this. Right? Now, remember how we define the AI. It's the derivation at the J coordinate function. So this is equal to AJ. Okay? So the derivation applied to this function gives me this. Is that clear? Okay, now, let's see what happens on the right-hand side. If you apply F, because remember this is here. So now it remains only to apply F to the right-hand side. And what do we have? Exactly this. AJ times the partial with respect to Rj of F. And we're done. Okay? Any questions? So we proved that this is the dimension, but moreover, I think it's important to stress that we have a standard or canonical basis given by the partial derivatives of the n variables. Right? So here it is. So that's the important thing to remember. Now, let me make another observation. Okay. If you have an open set, you have the same. And I mean, basically, I could have given that all the way from here, right? Because we already know that this is the same for Rn and U. So just by this definition, I can replace this by U, because they are the same, not what we said earlier on. So the tangent space at a point in an open set is the same as in all of Rn. In particular, you have the same generators for TPU. Any questions up to this point?
No, it's fine.
Now, so note that we have defined this space in a purely algebraic way. Okay. I will express that out in a moment. Okay, now what happens on a manifold? What will be the tangent space at a point, but now on a manifold? Well, we will need to define this as we did before. That's no problem. And again, if I have an open set in the manifold that contains P, those two algebras are the same. So the tangent space is the set of derivations, right? Nothing new. But now, unlike this case, what we have here is that Rn has a canonical basis or a canonical chart, the Cartesian coordinates or Cartesian coordinate functions. But on a manifold, we don't have a standard or canonical chart. So we cannot express this in a canonical way. It will depend on the chart that we use. So in order to have this description for a point in a manifold, we need a chart. So take a chart about P, and then that's the tangent space now. Okay? So note that the right-hand side depends on the chart. The left-hand side is the definition, the set of derivations. And the way to get that is exactly by recalling our definition of the partial derivative. If we have a smooth function on a manifold, then on a chart we define the partial derivative that depends on the chart. And this is the definition of that. Right? So assume that you have your open set on a manifold. You have your chart. Do some open set in Euclidean space. I'm considering all of Euclidean space. And we define this function, the coordinate functions on U. So what's the idea? If you fix all of the entries in Euclidean space and you only vary one entry, you're like moving like this. And that's how you give coordinates in the chart. You're moving like this. If you move in another direction, then you might be moving like this, right? Okay then. So we know that in Euclidean space, the tangent space is generated by these elements, and they correspond under the definition to these elements that we have here. Okay, so this was the algebraic definition of the tangent space at a point. And again, this can also be thought as in U where U is open. Okay, so now I'm going to give the definition of the tangent space, which is shorter, in a geometric way. But this is very important. So the tangent space is the set of derivation on the terms of functions at P. Okay, so again, I'm going to consider Euclidean space. And for that, in calculus, the tangent space of a point, it was just to consider vectors where the initial point is the base point. Okay? So here P is the base point. So that's how you define the tangent vectors at P in a geometric way. An arrow where the initial value is, or the initial point of the vector is at P. So they are all anchored at P and you can move in any direction. And in that way, it was very clear to you that the tangent space is a linear space and has the dimension of n. Okay, so this is the definition that you might have seen in calculus. Now, this is something very important that I would like to stress. So, think that you are in Rn. Assume that your manifold is inside Rn, and you have a point in the manifold, which is here. Then, in a geometric way, the tangent space at a point is what you see as the tangent space to the surface or to the manifold inside Rn. Right? So that's something that you can think of as the tangent space to the manifold at a point, but when the manifold is inside Euclidean space. Now, this intuition is good, it's fair. So it's good to think about the tangent space in this way. However, there are a few things that you need to be aware, and they're very important. You see, when you think of the manifold inside here, and you define this to be the tangent space, be careful because for the manifold, give me a second. The manifold is inside Rn, but there is no preference if the manifold is like this or you move it like this. If you move your manifold, the tangent space at a point is going to be different when you move it to the other point. But the manifold is the same. So with this concept, the tangent space depends on how the manifold is inside Rn. So you have to be careful about that. For intuition, it is very good to think of the tangent space like that, but be careful about it. Now, again, I'm stressing that you are inside Rn. But remember that there are manifolds that do not lie in Rn, in principle at least. For instance, last time we saw this example of a manifold. And that one, it doesn't lie in Rn. It was a topological space, and we gave a smooth atlas on that. So you cannot think, oh, well, I can think about it in Euclidean space and have there the tangent point or tangent space. So that's why it is very good, the algebraic approach. You don't need that. Okay, but again, with the tangent space, in terms of a more geometric setup, in order to define the geometric, the tangent space in a geometric way, again, I'm going to consider Rn is just to consider curves and the derivatives. So P is a base point, and I play in this curve. At the J entry, I'm only moving at the J entry. Everything is the same, except on the J entry, I'm moving along that direction. So I have a curve in Rn. this curve at 0, it equals the base point, right? It is a smooth curve. This is just calculus. So then I can take the derivative of that curve. I take the derivative and I evaluate at 0. Right? Remember that the curve at 0 equals p. So I take the derivative and I evaluate at 0 and I get this. This is just calculus. And exactly this vector that you get is what it corresponds to this vector. To ddrj at p. So this is precisely in Euclidean space in this direction. Is just the derivative of that curve at the point. In fact, I mean, the image of that curve is a line like this. Okay, so this is a geometric way of thinking about the, well, we lost someone, we lost Jesus. So let's wait a few moments to see if it was a technical problem or he decided to vanish. In the meantime, Moises, any questions?
So far, so good.
Cool. So, Ahmed, I don't know if he switched to YouTube or something.
I will try to contact him. However, let's see what he says.
So, let's see. Jesus, if you are on YouTube, just let me know so we can move on.
I think his internet went down. Because
Pardon?
I think his internet went down since my
Right.
messengers are not getting up to him.
Okay. Also, now he's here. Okay. So he's connecting now. You're back.
I'm sorry.
Okay.
I lost my connection.
Yeah. No. That's okay. So again, so what I was saying, this red line is the image of this curve. I know that at 0 is equals p. And so the derivative, which is this vector 0, 0, 0, 1, 0, 0, is the green arrow that I wrote here, where the initial point is at p. right? So so the result of the derivative is what we call that derivation, ddri. So in geometric ways is that vector, and in our previous discussion, it corresponds to the derivation ddrj. Right, so ddr1 is the vector 1, 0, 0, 0. But again, I mean, I want to express out that those vectors, you are thinking of them they have an initial point at P, right? 1, 0, 0 will be this one, and so on. If P is another different point, I have those vectors, right? Okay? So that's a way of thinking about the tangent space of a point in Euclidean space in terms of these particular curves and the derivatives. Now, on a manifold, if we would like to take this approach to a manifold, what we do, we take a chart, okay? And exactly the same thing. What I did above, I was taking this curve, only moving in one direction. So it's defined on R. On 0, I will go to this point that later on will map to P, right? This path will give me a curve on the manifold. So this is the curve on the manifold that at 0 equals P, but now P on the manifold, not on Euclidean space. At 0 I have here, or at 0 in Euclidean space is this one. And remember that the derivative at 0 in Euclidean space gives me this vector, which is ddrj, and that corresponds by the way that the coordinate functions are defined on U, and by your definition of the partial derivative with respect to this chart to ddxj. Okay, so this is what we have now. Okay, so up to this point, I'm done with the geometric approach to the tangent space. We saw the algebraic one and the geometric one. It is important to realize that we can define the tangent space in the algebraic way, that we don't need to see the manifold inside Rn so that you can imagine the tangent plane. And so the tangent space is just the set of derivations on the germ of functions at P. Okay, any questions? Okay, so let's move on. Now that we have defined the tangent space of a point, I would like to put you on the spot and think about this for a while. So what we have is, at a point in a manifold, I've assigned a vector space, okay? Think about it this way. To a point, I have assigned a finite dimensional vector space, okay? It will be irrelevant, but let's say that it is over the reals. Now, if you're given a vector space, how can you come up with new vector space out of that one? Or what can you do with that, with a vector space? Any other algebraic objects that you can construct from a vector space?
Like the dual?
Is dual, right? More? I need more. So we have the dual, okay? Only that one? Come on. Okay, you guys need to study more. Remember GLV, right? The set of all linear transformations from V to V that are invertible. That will give you a group. What else? Like for instance, what you saw in multivariable calculus, and also you were supposed to read the first part of the book. You have the K-stereo algebra of V, right? You can do that. You also have the tensor V and V. Also, you can do, so we have the alternating, but you can also do the symmetric algebra of the vector space. And many more things that you can do. Let's say if you have not only one, but two vector space. So I will put something like this. And also the endomorphisms of V. Linear math from V to V, but they don't have to be invertible, right? That will be a vector space that contains this group. Okay, so there are many things that you can do in an algebraic way with a vector space. I only put a few of them, and they will be relevant further on, further ahead in the class. Okay, so I want to finish that part about what you can do with a vector space. Okay, now, so far we have defined for every point the tangent space at that point, right? So this is what we have. And now we will move on to define a vector field on a manifold. Okay? So first of all, I'm just going to say vector field. It will mean a function. But later on, every time that we say a vector field will be smooth. Like in this context, every time that we say a function is assumed to be a smooth function. So let's define a vector field on a manifold. So it's going to be a function from the manifold to the set of all tangent spaces has p varies in the manifold. But the function is restricted that at a point, it has to give me a vector on that tangent space. Okay? At a point, I assign a vector on that tangent space, not at any other tangent space. Okay? So, right here, permítame un momento. No. So, sorry. I only wrote function because this is a manifold, so it will make sense eventually to say a smooth function. But here, I don't have a smooth structure. So far, this is just a function on sets. So that's a vector field. Now, you have seen this in multivariable calculus. So it is just arrows, or more explicitly, for instance, in R2, you have that one like that. I'm sure that's the notation that you use, but you can be a little bit more precise. And that means that at the point xy, and I just want to emphasize that it is this vector on that tangent space to that point. Okay? And this is the plot of that vector field in R2. All those arrows. It is a constant vector field. Another one that you might have seen is this one. And again, if sometimes you can write it like this just to be more precise about the point. But here we have non-constant coefficient as opposed in the first example. And you can also plot this vector field here. Right? So at the origin, you have the zero vector, and then if you move at the point 1, 0, note that you have this one, right? Yeah, because y is 0, so you don't have this one, and you only get this one 1. So you can check. So this is what you get at 2, 0, 0, 1, 0, 2, and so on. You can plot the vector field on R2. Okay? These are examples of smooth vector fields, and this is something that we would like to make precise, because so far we only have a function. So we have a vector field, a function. At P, I need to get a vector in here. So remember that this set is the set of derivations. So I hope I have a bunch of derivations on different germ spaces. Okay? Now consider a smooth function. This is a derivation, right? So in particular, if I have this function, note that this function induces an element on the germ of functions. And this is a derivation, so I will get a number. Right? But now, if I say that P varies in n, this will become a function on n. A ver, un momento, por favor. Any questions up to this point?
No, not yet.
So, given a smooth function f and a vector field, I get a function. Okay? Because now this point varies, so I get a function. And now I can say what is the meaning of a smooth vector field. Recall that here we don't have a smooth structure, we only have smoothness here. But still, we can say, what do we mean by a smooth vector field? So the resulting function must be smooth. For every function, this has to be smooth, and that's how we define a smooth vector field. Okay, so that will be the definition of a smooth vector field. Later on, we will not do this today, maybe tomorrow or next week. this space, we are going to give it the structure of a manifold. And then the definition that I just gave about a smooth vector field is going to be equivalent to say that this function is smooth. But that will be for later. Okay, so consider a chart. Okay, I have a chart about U, and I have a vector field on N. I just want to see or to understand the vector field on the open set of the chart. So on U, the vector field looks like this. Okay, so these functions are functions only on U. Because we already saw what is a basis for the tangent space at a point. So at every point of view, I have a derivation, so I can write it down this way. And it is the same notation as this. Right? And this is only on U. Because on U, I only have those coordinates, x1 up to xn. Then we can be more precise about what is a smooth vector field on U. So take a vector field on N and a chart. So the vector field looks like this. And the vector field is smooth on U. And I only have U because U is my chart. If and only if the functions are smooth on U. And so it is going to be a very straightforward understanding of what it means to have a smooth vector field. The coordinate functions have to be smooth. Okay? Let's prove this. Let's consider the coordinate functions of the chart. Remember that we have seen that those functions are smooth. So, because the vector field is assumed to be smooth on U, this is a smooth function on U. Okay? Now, what happens when I evaluate this function on this vector field? So we're just taking the partial of xj with respect to xi. And it will be 0 or 1, depending if ij agree or don't. So in that case, I only get f of j. Okay? And well, I only prove one direction. You can work out the other direction. Okay? So locally, a smooth vector field is going to have smooth functions as the components. And it is with respect to the chart x1 up to xn. Now, here is when I want to make this more precise. One of the reasons that we talk about C-infinity functions is because when you take the derivative, you will also get a C-infinity function. Okay? But and exactly on vector fields, this is what we have seen. If I have a vector field and a smooth function, I'm saying that this is a smooth function. But if we consider something weaker, the smooth function, let's say fk, and my vector field is this one, I'm going to get 1 degree lower of regularity. So in that way, we will have to be more careful about what is the regularity of the function, because it can decrease. And when we have smooth functions, we don't worry about it. We can take a derivative and it will also be smooth. And we can move on with no problem. But if we take a k regularity of the function, you have to be careful when we apply it to a vector field, because the regularity will decrease by 1. Okay, so that's something good about having only to deal with smooth functions. Okay, I'm going to use this notation. It's the standard notation for the set of smooth vector fields on M. Okay, so I have there the set of smooth vector fields. So remember, if I have a vector field and I fix a point, I have a derivation. So we are passing from the point object to the global object. Derivation was in 1 point. Vector field is global. So for a vector field, this is the extended of the product rule. And this is what it is called, the Leibniz rule, or the product rule. Right? This is a function. This is the product of functions. Again, product of functions. Or when you evaluate that function at P, it looks like this. So this comes from the definition of a derivation that we have at the point, the product rule. But now globally, it is Leibniz rule of the derivative. Now, the set of all smooth vector fields is a vector space. So this is how the sum of vector fields is defined. Right? So here, this sum is the sum on this vector space. Right? So that's this sum. And the same for the scalar product. So this is the definition of the sum of the vector fields and the product. In this part, I put lambda a real number, but you can actually do something more general. You can put a function. You can take a smooth function and then you can multiply. That's also true. I didn't wrote it like that because at this point I'm making an emphasis on the concept that the set of vector fields is a vector space over the reals. But keep in mind that you can put a function here. Now, the other thing is that, so this is a vector space, but it happens that it is huge. Okay. This is an infinite dimensional vector space. We will see that next time in class, and maybe this is going to be useful. Okay. So up to this point, my time is up. So vector fields is a global thing, and a point is a derivation. Those are the elements in the tangent space. Right? I don't know if you guys have any questions. No? Everything is
No, I
clear?
don't think so.
Okay, so we will continue tomorrow. Maybe I will draw some examples of vector fields. But the one that you know from calculus, that's very good. One thing very important of vector fields, just like the knowledge that you have here, is that it is very easy to give any example of vector fields. Use whatever knowledge you have from calculus, and you can give a vector field. Okay? So that's something very good. And now, so for homework, I would like you to look at the notes of differential equations, because we will use something very important, which is the existence of a solution of an ODE, or a system of ordinary differential equations. That's going to be very important, because from a vector field, we are able to obtain a diffeomorphism. And again, I mean, even in R2, I can ask you, give me an example of a diffeomorphism in R2 or in Rn. The first answer that you can come up with, in R2 at least, is rotations. You have studied that in in your geometry class. You have rotations, translations, I don't know, reflections, all of that. This example is related to the diffeomorphism of rotations. But vector fields are going to help us to obtain diffeomorphisms, which are much harder to come up with. Great. So I will see you tomorrow then.
Right. See you tomorrow.
Right? Okay. Bye.
Nice day.